Thanks, Mario. Thanks again for the invitation to this great seminar. This is my second time I'm speaking. I find it slightly amusing that that also this time it's similar than the first time, so that I have this new concept and I use most of the time to introduce the concept, so that there will be lots of definitions coming, but I hope that's fine. I think kind of the little bit unfortunate part is that I don't have that many pictures, so the pictures would have made a whole difference. But what I'm gonna talk about today is a joint project we had with Zhiqiang Li and Hanyun Zheng, and this is something that that I actually already talked about almost or perhaps a bit more than a year ago. But then actually Hanyun had a great insight to the setting, and then we started to develop a totally new things based on his observations, and this led to this notion of kind of Thurston-type maps. So that what I would like to talk today is a little bit of kind of what is usually done in 2 dimensions, so the Thurston maps, which are very familiar to this audience of this seminar, but I want to talk about the higher dimensional version of that. So, but let's have the starting point, so that the slide is slightly covered, but let me say that now the theorem on the top of the page, which has this kind of blue framing, so that this will be repeated on a couple of slides. But I want to have that kind of as the staple theorem. I will start the talk, so that the things we consider, they go back to Haïssinky-Pilgrim and then Bonk-Meyer, and there's this kind of dynamical characterization of rational maps, and this starts that you have an expanding Thurston map on a topological two-sphere, and then you make a visual metric for the Thurston map, and then it turns out that the visual sphere is quasisymmetric to the standard sphere if and only if the map is topologically conjugate to a rational map. So the topological conjugation is kind of here in the right side of the slide, in the slide diagram, meaning that you can reparameterize the metric sphere and get a rational map on the Riemann sphere. And then the Thurston map is on the left-hand side, so that a map is a Thurston map if it's a branched cover. And I wanted to give the definition because I wanted to say that from now on the branch covers for me, they are really discrete and open maps, so that typically the map is orientation preserving also and this type of things, but so that you know that on the surfaces, what you can think is that you can think these mappings which are locally modeled by a z to power d, but let me go a little bit more topological and say that we look discrete and open maps. And then you put the degree that you want to omit homeomorphisms, you say that the degree is at least 2, and then you say that the kind of the key thing is that you say that the map is post-critically finite, meaning that you take the branch set of the map, so BF, here the set where the map is not local homomorphism, and then you take the forward orbit of that set, and you want that this infinite union turns out to be a finite set. And if that's your case, then you say that your map is a post-critically finite, and you say that your Thurston map that your map is a Thurston map, which is a post-critically finite branch cover of degree at least 2. And let me just put a little side remark here, so that I stated this for closed surfaces, but that's a slight overkill in this setting, because if you assume that you have an interesting Thurston map, meaning that you really have some non-empty branch set, then the kind of the classical Hurwitz formula counting arguments show that your surface is actually a topological sphere. So that if you allow that your mapping if you allow that there is no branching, then you have a covering map, and then the interesting cases are the torus, but let me not go there. Okay, so why I want to have the comment is that in this case the two-sphere is the right context. Okay, but so that somehow for me and for Zhiqiang and Hanyun, the starting point was that, okay, what is the role of dimension 2 in this statement? So there are really kind of, so that if you look the statement, actually this visual metric part has really no relevance. That can be done there's no kind of dimension dependence there. And the quasisymmetry is also dimension independent thing. So then it really comes to question that, okay, when you want to define the Thurston maps, what happens then? So if you go to higher dimensions and you take a post-critically finite branch cover, so you take a discrete and open map, you look the branch set, the set where the map fails to be a local homeomorphism, you force that the post-critical set is finite set, then your class of mappings collapse to covering maps. There is no branching after this finiteness condition. And the reason is really that because if you are, I didn't write the full reason, but what you have is that when you take take out the branch set and the image of the branch, and you take everything related to branch out from the manifold, if it's a finite set, then it doesn't change the fundamental group. And the reason is really that because if you have a finite set removed from an n-dimensional ball, then it stays simply connected in higher dimensions. And then because you have a covering map, then you can argue you can start to count the degree of the map, and you end up with locally you end up with homeomorphisms, and in the end globally you get a covering map. So that what is really kind of the if you try to mimic the definition directly, then the Thurston maps really the whole class collapses. And but if you look the statement of the theorem, there's also another place where the two-dimensionality kind of comes in, and that's the definition of the rational maps. Because if you have a rational map and you take a ratio of two polynomials, then you better be able to kind of divide. So what you really need is that if you start to look this formula, then you need to come up with the counterpart what you actually want to have there. So that I know that this is slightly silly explanation, but if you really think the statement formally, you notice that you also, so that it's not only the Thurston maps you have to replace, you also have to replace the rational maps. And this is kind of the starting point of this story. So that what we have is that we have these two questions. So what are the counterparts of Thurston maps on higher dimensional manifolds, and what is the counterpart of rational maps in higher dimensional manifolds? And somehow the rational map part is much easier to understand. Or kind of that's somehow we already have a blueprint what to do. So that if you look the work of Haïssinky-Pilgrim, which is the Asterix book, so you notice that there is a metric characterization of kind of, I put the rational maps into quotient kind of quotations, because kind of I'm going to higher dimensions and I'm already kind of trying to find a replacement what to use. So if you are in higher dimensions, you are looking at maps on a closed Riemannian manifold. Then there is already a class which is so-called quasi-regular lattice maps. But what Peter and Kevin proved, they proved that this is actually characterized by so-called metric coarse expanding conformal class, so the CXC maps. So that this, if you now have this type of have these two theorems in your hands, you notice that okay. So that the rational maps, which are kind of under iterations, they are holomorphic maps. They stay under holomorphic under iteration, so there is no buildup of distortion. And then the quasi-regular lattice maps turn out to be the maps where you have the same property in higher dimensions, so that there's a little bit of distortion, but not a buildup. So then you might want to take this as your kind of second candidate. So what for the counterpart of the rational maps in the theorem above. Of course, this leaves still open what is the counterpart of kind of Thurston map, so that this is still have to be discussed separately. And that's kind of the main point, but let me first say what are these quasi-regular lattice maps. Oh, sorry. Okay, sorry. So the one thing I wanted to say at this point is, okay, why this is interesting? So why we want to consider this? So I think my personal interest to this problem or this question was kind of perhaps completely different from many other for many other people because so previously with Yang-Mei Wu we worked on higher dimensional metric spheres and the uniformization problem for them. And for me, this theorem of Haïssinky-Pilgrim Bonk-Meyer, I think for me it's very exciting because what you have is that you have a dynamical metric, and then you can actually characterize the quasisymmetric class using the dynamics. So that if the dynamics turns out to be kind of standard type dynamics, then also the metric sphere turns out to be a standard sphere. And I think kind of this should be kind of contrasted in the higher dimensional setting in the sense that if you look kind of the literature from the 90s, you look works of Sems and then a little bit later Hanyun and Wu and so on, you notice that if you start to work on higher dimensional spheres or other higher dimensional kind of model manifolds, you notice that there are only negative answers available in the literature. So that in 2 dimensions you have the Bonk-Leiner theorem saying that the qualitative properties of the metric improve to a good parametrization, but all of these things are kind of canonically killed in higher dimensions. So it would be so that for me this question about having a visual metric where you can kind of characterize the quasisymmetric class, this was very exciting because now you have a way to talk about the positive results, and this was the kind of my angle to this higher dimensional question. My co-author, on the other hand, is much more interested in the Sullivan dictionary, and he was somehow I think for him, so that for Zheng, so that the question was that we have also in this seminar we have quite many times talked about the Sullivan's dictionary, where you compare the properties of Kleinian groups to the properties of complex dynamics. And then if you start to ask a question that what is the higher dimensional Sullivan's dictionary, you notice that, okay, you can still have the Kleinian groups and you have that side in all dimensions, but when you go to the dynamic side, then comes the question that what is the corresponding dynamics. And then for this reason, it becomes interesting to consider the counterpart for the rational maps here, because the original theorem what we have here. So in the 2-dimensional theorem, this corresponds in the Sullivan's dictionary to the Cannon's conjecture. So there is this type of background here, but I don't want to really. I'm not an expert in that, and so that there are many more who are in the audience who know much more. So that I will just leave it as such a remark. Okay, but now the UQR maps. So the starting point is that I think kind of this is also very familiar to many in the audience, but let me just say a little bit. So that the quasi-regular maps, they are considered to be the counterpart for higher dimensional holomorphic maps in the complex in the conformal geometry of kind of Riemannian manifolds. And then how you see that is that the distortion inequality here, where you compare the differential, operator norm of the differential to the Jacobian of the map. That's a relaxation of the conformality. And but from dynamical point of view, this becomes interesting when you iterate, so that the question is that a priori the distortion constant grows when you iterate, but if it stays bounded, then you say that the map is uniformly quasi-regular. And this is an interesting class, and it was only in the mid-90s when Ivanits and Martin came up with the first interesting examples in higher dimensions showing kind of branching behavior for these uniformly quasi-regular maps, and in that sense, so that the map the maps kind of actually Gavin Martin likes to consider them as really as rational maps on the higher dimensional spheres, especially, but this is kind of somehow what you can consider some counterpart. The reason why I really like this class of maps is that if you take these uniformly quasi-regular maps, you have the same property what you have for quasi-conformal groups coming from Sullivan and Tukia, so this is actually then a result of Ivanets and Martin saying that you can actually find a measurable conformal structure which makes for the manifold where the map actually acts as a kind of branched conformal map, so that you can actually there is a kind of an inherent natural geometry for these maps, and that's a kind of the original reason why I really got interested in these maps. Okay, but that's kind of the general background, and then the kind of what we are kind of considering here is the quasi-regular lattice maps, and so these are really the same lattice maps what you see in in 2 dimensions. The only exception is that when you are going from the Euclidean side, where you have the action of the affine map, then when you go down to the manifold, then the condition is that the mapping going down the phi, the phi is a quasi-regular map. So that instead of having their holomorphic, you put their quasi-regular. Otherwise, kind of the properties of the groups and how the affine map A and how the subgroup gamma and how phi how they kind of work together. This is the same as in 2 dimensions. And now I noticed that I think I have the accent perhaps in the wrong way. I'm sorry about that. Okay, but this is kind of the starting point. That this is saying that there are kind of higher dimensions there are maps which we can kind of consider as a replacement for the rational map, and that way now the burden is really in understanding the Thurston. So what we can say about the Thurston maps, and I think kind of so that the pain we kind of observe here, I think kind of that has to be explained a little bit before I go to the actual definitions. I think kind of what should be somehow said that okay, so we know that these quasi-regular maps we just discussed, they are discrete and open maps, so they are branched covers in our discussion. Then the kind of the classical theorem about branch covers is a kind of Chernovsky-Weisseler theorem, saying that if you have a discrete and open, it's not self-map, but a map between connected and oriented N manifolds, then the branch set, the set where the map fails to be a local homeomorphism, this has topological dimension at most n-2, so that it's two dimensions lower than the ambient space, and the mapping becomes immediately orientation preserving or reversing. So that there is this, so that the branch set what you have for the map, it doesn't separate the space, it is a small set, but the only thing you know is really about the topological dimension. And that's where the comments kick in. So in 2 dimensions, you can show that the branch set is a discrete set. Not so that you can improve the fact that it has 0 dimension. You can improve it to a discrete set, and this follows from the Stoilov factorization and this type of classical results. But then, when you go to starting from dimension 3, then I would say that practically the kind of the structure of the branch set is not known, and I think the situation is pretty much the same now what it was during the time of Heinonen's ICM paper. I think 2002, if I remember correctly. So because he in his ICM paper he wrote several questions about the structure of the branch set, and I don't think any of those has been actually answered. I think kind of the only thing what has really happened after that is that things have in some sense gotten worse because Hennen and Riemann created these examples of quasi-regular maps where the branch set is branching, and the examples are actually such that the branch set is, so these are 3-dimensional examples. The branch set consists of infinite 1-dimensional complex which converges to a wild Cantor set. So that which says that you cannot really hope anything kind of, so that any easy description for these branch sets. They are, and in most cases you can only consider them as topological objects. And if I now think about our kind of dynamical setting, so then you would kind of it would be somehow nice to kind of hope that when we are in a dynamical setting, then the branching cannot be that difficult, and perhaps we have some gain coming from the dynamics. But actually, Martin and Peltonen killed this hope totally, so that you take any quasi-regular map on an n-sphere, and then they create a uniformly quasi-regular mapping with the same branch set. So then, for example, this Heinonen-Riemann monster branch set can be realized as a branch set of a UQR map. And now you kind of, so that you don't really have any kind of a nice combinatorial structure for the branch set to start with. And all this was kind of motivation, because this is what we actually want to do. So let me now kind of take a kind of one slide, a little bit before the definition, so of the Thurston-type map, and kind of try to motivate from a different point of view that what we want to do. So perhaps those who have been involved in proving these theorems, perhaps they covered their eyes because of the very short description of the kind of the strategy. But let me just say that if I think about this uniformization theorem in 2 dimensions, so what you can do is that you take this expanding Thurston map. I haven't defined expanding yet. I will do that later. But you take this Thurston map, and you can think that you have a 2-sphere. And you have your post-critical set on your 2-sphere. It's a finite set. And then you, for example, put a Jordan curve going through all the points in the post-critical set. And then the Jordan curve decomposes the 2-sphere into 2 cells, two cells. And then what the expanding kind of does to you, so that if you start to pull back this cell decomposition, you will get a shrinking sequence of cell decompositions on the S2. This will give you a rise to a visual metric. And then when you have a visual metric, there is a ... because then you have the real proof, real things happening, and then you get to the uniformization. But why I wanted to highlight it in this way, because when you do it in this way, you notice that the cell decompositions will lead you to a visual metric. And then, so that if we think that this is a one way to go from totally topological situation, which is the Thurston maps, to a metric situation where you have a visual metric. So then the question is that, okay, the idea is that, okay, how about if we try to mimic this philosophy also in higher dimensions? And this is let me not define the cell decompositions. I have a picture, and I try to explain the picture. The terminology here is that an N cell is a topological space which is homomorphic to a closed Euclidean N-ball, so that it's really the kind of the familiar space we all know. And it is just a topological copy, so that allows us to draw pictures than what we have here on the right. And then when we have a cell decomposition, so what do we do is that we take our space. Here in the picture it is the n-sphere. And then what we do is that we cover the space with n cells, with the kind of the top dimensional cells, in such a way that their interiors are disjoint, so that they overlap only on their boundary. And so that why I'm saying that these are cell decompositions and not something more kind of precise like simplicial complexes or triangulations or something like that. So that what happens on this level is that these n cells, they don't really come with simplicial complex structure. So that what you have is that the boundaries of the n cells, they consist of n-1 cells, and then you can go to lower dimensions, and you always in the intersections you will see kind of lower dimensional cells, but as in the picture, so that these cells don't form a complex in a sense that if you think that you have here this a red cell, which is here kind of I'm kind of drawing saying that it is a homeomorphic to the closed end ball, so that now you have these blue cells inside, and the boundary between the red and blue, it actually kind of, you can see that it consists of many one cells in this picture, so many line segments, and so that what we don't require is that if you have two n cells, then the intersection is exactly an n-1 cell, but what we want is that it is a union of n-1 cells. So that now you see that we are having a combinatorial description, but it's a little bit weaker than what we usually have. But I wanted to say kind of this in picture because the next slide is already quite technical. Okay, and now we come to the version of the Thurston map. So that perhaps it's a kind of good place to start is the middle, in the middle of the page there is this very small definition saying that the branch cover is a Thurston-type map if it is CPCF and has degree at least 2. So now you notice that if you just remove the dash type and you remove the first C from the CPCF, you notice that you have the original Thurston map definition. So, but then comes the question that what is the CPCF? So, and for CPCF for us is abbreviation for cellularly post-critically finite. And before we actually look at the definition more carefully, so that what is kind of the idea here is that I have been kind of a little bit kind of going through the slides pretty fast, but the point that I wanted to make earlier is that the problematic, so that when you want to extend the definition of Thurston map to higher dimensions, the problem was that the post-critical finiteness condition is way too strict, so that you just cannot take finite sets of points and then discuss the behavior using them. You need to use larger sets. But then we know that if you look branch sets of higher dimensional branch covers, then the sets are larger, but then they don't have structure. So what is kind of the idea of the definition is that we are putting a finiteness condition for the post-critical set using these cell complexes or cell decompositions. So so let me now kind of say what we actually want. And so that the key starting point is that you take the post-critical set, which is again the forward orbit of the branchet, and then you assume that there is a finite cell decomposition on this set, so that you have this so that the post-critical set PF. So actually now I noticed that okay, I didn't put the dimension here, so that the dimensions here, so that the manifold itself, let's say that that's n-dimensional. And the cell complex we use has dimension n-2. So I want that the cell complex I use is the topological dimension of the branch, so that I don't want that the post-critical set is anyway wild in this sense, or kind of space filling or anything like that. So I have finitely many cells of dimension at most n-2. And then I cover my post-critical set using these cells. And what are now the properties? So what is kind of the first difference to the 2 dimensions? In 2 dimensions, when you have a finite set on a surface, you can just move around the finite set with homeomorphisms as you please. They are somehow in a standard position all the time. There is no kind of no configuration is really special from topological point of view. But if you go to higher dimensions, let's say that you are in 3 dimensions, you can easily, there are classical examples of embeddings of line segments into the 3-dimensional space, which are wild embeddings. And this is of course something that if you if you have to start by discussing this topological issue, then you are really in deep trouble, because then kind of this theory gets extremely deep immediately. So the first condition, what we want is that we have our cell decomposition for the post-critical set, but we want to be able to refine it so that to chop it into smaller cells in such a way that the smaller cells we see, they extend to a cell decomposition of the whole space, so that the cell decomposition, which is this kind of script P naught, is a kind of codimension 2 cell decomposition in the space, but we want that actually that cell decomposition can be realized as a kind of n-2 skeleton of a cell decomposition of the whole space. So we want to kind of that the things are standard from the point of view of the whole space. This is the upshot of the first condition. And then there is the Markov, which is saying that now kind of we have a mapping, so that if we look from the point of view of the post-critical set, we want that when we have chopped up the cells and we map it with our mapping, then they map the cells map to cells. So that then what we so that we have this kind of so that here what we're saying is that we have a refinement of the cell decomposition script P, and that the mapping is a Markov, has this Markov property with respect to that refinement. So this is kind of the first condition. The second condition is a little bit of a technical condition, but then when you start to work with these things, then this is very handy to use. So the reason is that we want that the cell decomposition P we start with, it is natural from the point of view of the branching of the map, so that we don't want to, so that suppose for example this type of thing that you kind of in 3 dimensions you have 2 axes which are intersecting, and then you wind around one axis and wind around the other axis, and you notice that in the origin you have kind of the winding is going to 2 different directions, and that affects the local degree and all these things. And so now what we want from the cell decomposition is that the cell decomposition is natural from the point of view of these 2 intersecting line segments in my example, so that we don't have a situation that we have a kind of one cell going through the interior of the other cell and causes us jump in the local index of the map and things like this. So that what we really want is that the P is already such that we have chopped up things enough so that all the interesting behavior of the local index happens on the boundaries of these cells. So that's the technical thing. And this is actually the part where I say that I'm sorry that I don't have enough pictures, because so what are the examples, so that you can take you can go so as we did, so you can go to the book of Daniel and Mario, and you start to look kind of the pillow maps, how they behave in 2 dimensions. So let me just recall that the pillow map is that you take two squares, you glue them together along the boundary, and now kind of if you build a flap space over a pillow like that, and if you do your flaps correctly, you can have a branch cover or a Thurston map to this pillow. So that what you have is that you can build these Thurston maps using these combinatorial descriptions. So now when I said that, so if instead of taking two-dimensional squares, you take higher dimensional cubes, you glue them along the boundary, you can do exactly the same kind of flap spaces, and that gives you a class of examples. I think kind of from the point of view of what we have been doing here, so that for our project, there is actually a kind of there's an interesting kind of a related paper by Zhiqiang and Hanyun, where they show that these so-called orthotopic quasi-regular lattice maps are these Thurston-type maps. So that when you go to the definition of a quasi-regular lattice maps, there is a group, there's the linear map. So orthotopic here refers that that actually the group is such that the fundamental domain of the group is a rectangle, and then the linear part is just scaling, and which leaves actually the quasi-regular quotient map as the kind of the free variable there, so that there's a class of maps like that, and then then Zhiqiang and Hanyun they show that in this class the kind of the CPCF condition holds, and it is actually an open question whether it holds for all quasi-regular lattice maps, and I would say that the issue with quasi-regular lattice maps is really in the quotient, so that we don't really understand well what are the possible quotient maps in the picture, and this is causing us trouble. There is actually a very nice paper of Ilmari Kangasniemi from some 5 years back where he studies what are the possible groups and how they work in this case, and I recommend that as a nice night reading for everybody. Okay, but this is kind of so that this is the setting. I know that the actual definition is kind of a mouthful, and we don't really need it later on. But I wanted to show it because this is kind of the setting we have to work with. Okay, but let's see kind of how we now use this. So we go with the strategy. Oh, sorry, there's one more slide, which was the result. Okay, because now we have all the players. So now we can formulate the theorem. So that what we have is that we take an expanding Thurston map, expanding Thurston-type map. So what we defined on a previous slide, the expanding is defined on kind of this slide. We take it on a closed Riemannian n-manifold, and then we take a visual metric for that dynamics. So that the expanding is here in the first definition of what we have. The expanding means that you have a cover on the you can find a cover on the manifold in such a way that when you take the pullback covers, iterated pullback covers, meaning that you take the premixes of sets and then you take components, you get new covers, then the mesh of those covers go down to 0, and the mesh is the diameter is the supremum of the diameters of the sets. And then the visual metric is now built using, for example, with a cover like that, so that you find a metric which has the property that it's comparable to a kind of length scale which is coming from the separation level, so that you have this parameter c and alpha. C is a multiplicative parameter, lambda is really the key, it's the scale parameter, and then you say that you are looking kind of you're looking for 2 points, you're looking kind of the level that they are getting to the different sets in these covers, in these pullback covers, and then you want a metric which kind of corresponds to this scale information you get. Okay, but that's kind of the setting of the theorem, and then the statement is that so now the identity from the visual metric to the standard length metric coming from the Riemannian metric is a quasisymmetry if and only if the map is a quasi-regular lattice map, and that's so that now we see that the change to this theorem we had in the beginning is that we, instead of Thurston map, we have a Thurston-type map, and then instead of rational map, we have a quasi-regular lattice map. So that's kind of the setting, so that but now there is also something that, okay, so there's a kind of something that I didn't mention, because in the two-dimensional theorem we had the two-sphere. And then I said that, okay, that the theorem becomes interesting when you are on a two-sphere. Now we have a general closed Riemannian manifold, and now you may kind of also get the feeling that perhaps this is not the right kind of that. How general is this class? So just as a little bit as a side remark, so if you take this theorem, what we have here, and you combine it with the cohomology embedding result of Kangasniemi from 21, you get, and then you combine that with the recent result of Manin and Prives, you get that the class of manifolds which support, okay, sorry, now the statement, sorry, I forgot from the statement that the statement should read, suppose there is a Thurston-type map, from M to N on a closed oriented Riemannian manifold for which the visual metric is quasisymmetric to the standard. So that there's a sentence missing in the middle saying that if you get a standard kind of quasisymmetrically, if you get a quasisymmetric uniformization for the visual metric, then you have the embedding result for the cohomology, and the fundamental group is virtually abelian. Sorry, I forgot the punchline of the key assumption of the corollary. But what happens here is that we don't know exactly, even after this, what are the possible manifolds. We know that in 2 dimensions, of course, we go back to the original result. In 3 dimensions, we have a classification for manifolds admitting UQR dynamics, and we can use that. But in dimension 4, it is another result of Kangasniemi that the so-called quasi-regular ellipticity classification is not exactly the same as the uniform quasi-regular ellipticity classification. So what happens is that we know that there are manifolds. We know that the dynamics is now a lattice type dynamics, but we don't have precise classifications. Sorry for the messing up the statement of the corollary. It should really say that you have the Thurston-type map and you can uniformize the visual metric. Then you have these other properties. Okay, but now to the methods. Okay, so what is kind of the key? The key, so that if we look at the definition, there was the definition of a Thurston-type map, which I don't show you again, but I just say, there was this condition that you get this Markov type dynamics on the post-critical set. And what does that give you? It gives you that if you can actually start pulling back the information what you had using the map. So you started with this complex P, or this cell decomposition P, and then in the definition of the Thurston-type map, there was this P0 and a D0. And the D0, it was the decomposition of the whole space, and P0 was the decomposition of the post-critical set. But now, because of the Markov property in the post-critical set, you can pull back, you can take pre-images of the cells. So the pulling back is just taking pre-images of the cells, and you get a new cell decomposition P1. But that actually extends, because now the branching happens in this code, in this kind of n-2 skeleton. Also, the D0 can be pulled back to D1. So now you can kind of repeat this, and you have this kind of backward tower of cell decompositions. And so that what you can say is that, okay, if you have this CPCF map, then you have the cellular sequence like this, and then you have a cellular map. And now you can now you see that you are in the framework of kind of Bonk-Meyer. So you have a cellular sequence. Now you can you can construct the visual metric the same way that you do in the 2 dimensions. But what I find actually extremely interesting in this context is that from the visual metric, you get an intrinsic metric regularity for the original dynamics. Because the mapping, the Thurston map we have is just defined in terms of topology, so that it's just a topological definition. But when you have the visual metric, you have this lemma. So that you have this, that the mapping is actually uniformly expanding branched quasisymmetry. And so that, which is a metric property. With respect, when you are looking at the dynamics from the visual space to itself. So what is the branched quasisymmetry? This is something that this is a definition of Guo and Williams from about 10 years ago. And I used this with Jeff Lindquist earlier to study extensions of quasi-regular maps. But it turns out that this has a great dynamical counterpart here. So what is a branch quasisymmetry? So okay, we know in this seminar I don't have to define quasisymmetry. So what is the problem with quasisymmetry? Problem with quasisymmetry is that in order to have the definition, it immediately forces you to be an injective map. So if you want to study branch dynamics, you cannot have injective maps. But the great insight of Gu and Williams was that if you, instead of looking points, images of points, you look images of continua. You take two continuums, so E and F in my little picture above. You take two continua which intersect in this red point. What you can do is that you can map the continua over, and you can check what happens to the diameters of the relative size of the continua. So in my picture, the E and F are supposed to have the same diameter. So in this formula, the eta diam F divided by diam E divided by diam F is just eta of 1. And now kind of what we are having is that it is the inequality is saying that the images of the diameters of the images control each other. So if one is small, then the other is small. If you collapse a whole continuum, then you collapse every continua touching that continuum. And so that now you see that we have this very familiar type of behavior for mappings in our hands. And it is a relatively easy fact in the manifold setting to show that if your mapping is a branch quasisymmetry, or mapping is a branch quasisymmetry if and only if it's a quasi-regular map. And this because the manifolds are smooth, you can kind of, what you do is you essentially go back to Rickman's book and you start reading. So that's the idea. What Gu and Williams do, they do this in a much more general setting where you have metric spaces, and then they study the metric quasi-regularity, and their result is essentially saying that that in the metric setting the branch quasi-symmetries correspond to metric quasi-regular maps. But this is going a little bit too far for today. But I find this very interesting because I have spent essentially my whole adult life looking at this kind of QR maps, and now kind of this is a very simple looking condition to work with quasi-regular maps. Okay, but the dynamical version just comes that you essentially just use the covering argument. So that you assume that there is a cover, and you assume that there is this gauge function eta, and then you so that under iteration the mapping stays branch quasi-symmetry with the same eta. So that there is nothing kind of so this is very typical type of condition in this type of dynamics, where you just say that you assume that the distortions don't build up. Now it's just a metric version of that. And what you get is that this lemma, which I have here on top of the page, the same lemma, saying that if you have a uniform expanding branch quasisymmetry, this intrinsic property now actually gives you rather easily the fact that the visual metric is quasisymmetric to the standard Riemannian metric if and only if the mapping the Thurston map you are looking is actually uniformly expanding BQS in the kind of standard metric. So that the first one was in intrinsic way, but you can actually kind of the quasisymmetry between the metrics actually translates the intrinsic branch quasisymmetry property to a kind of the ambient or to the standard branch quasisymmetry property. And this was kind of the starting point of our. This was the first result first observation we made. But now we come to the full version of the theorem. So that the setting is that we are looking this. Actually, we can. Okay, I wrote here that we are looking expanding cellular branch covers. You can write the Thurston maps, but this is slightly more general. But you can think that you are looking Thurston-type maps, and you take visual metric for the dynamics, and then you have the following 5 conditions which are equivalent. The 1 and 2 are equivalent using the previous proposition, so that the visual metric is quasisymmetric to the standard is equivalent to the fact that you have a uniform expanding BQS map, meaning that you have this metric characterization for the dynamics. Then the third one is kind of the classical one, so that you say that you have a UQR map, so that your distortion doesn't build up under the stamp in the kind of in this kind of smooth framework. But then comes the rigidity, which is that the four saying that the UQR maps actually are these lattice maps. And then in fifth, I wanted to add here the metric CXC condition of Haïssinky-Pilgrim, because that actually comes into the equivalence in a natural way. So that how do we do this, or kind of how we work out this thing is that we because 1 and 2 are equivalent, it's enough to show that the 2 to 5 are equivalent. So what we do is that we start with 2 with uniform expanding BQS, and we prove directly from the metric property that these mappings are actually uniformly quasi-regular. This is not surprising, but they are conical, meaning that every point is a conical point, meaning that you can do a blow-up argument at any point. Then there's a classical paper, to me, classical paper from early 2000s of Martin and Meyer saying that if you can do that, then you are lattice. And then if you are lattice, then Haïssinky-Pilgrim say that you are then CXC. But then we do by hand, we go through the CXC, using the CXC definition, we show that we are back to this uniformly expanding BQS. So that this metric, here, actually this line of argument doesn't use the cellularity of the thing at all. So this is really metric and kind of a smooth discussion. Then we have the other line of thought where we start from UQR. Then we use the fact that we have this, I should say cellular. I wrote CPCF, but cellular is enough. So that you have this, you have the cellular structure for the mapping, and then that gives you that you are UQR map with the extra property that you have finite forward index, meaning that you take the local index of your mapping and it stays bounded under the iteration. And then when you have that, you get the conical property again. There's enough expansion then present in the map. And then you use Martin Meyer again to go to lattice, and then the lattice maps are in this context UQR. So the last step is trivial. So that you have these two cycles of arguments what you can do in this case, and it is kind of surprising that the actual structure doesn't really then so that when you have used your structure to go to this BQS level, then actually the other properties are really coming in a much more from a much more flexible machinery. Okay, I think I'm sorry I went a little bit over time, so I thank you. Thanks.
Okay, so let's thank Pekka. And let me start the discussion. So are there comments or questions?
So I have a question. So you had earlier that you don't really know what what M is, right? I mean, so you had this I guess by Eden
Yes,
and Mani,
poorly written corollary. Yes.
Yeah, I mean, you had that the homologies, the cohomologies, and the fundamental group is virtual. But I mean, okay, so but you in your theorem you have that there, lattice maps, right? So
Yeah.
I mean, do you actually have lattice maps that? I mean, okay, so I guess you can have them on a torus, but do you have other lattice maps that are not on the n sphere or what?
Yeah, so that there is a work on this. So there's a paper of Astola, Kangaslampi, and Peltonen, where they do kind of quasi-regular lattice maps in many in this kind of so that in the kind of the three-dimensional case, because it was okay. So the story goes that the when you look in 2 and 3 dimensions, it was known which are the possible targets, which closed manifolds are possible targets for quasi-regular mappings from R3. And in 2 dimensions, it's classical, and in then 3 dimensions, it follows from a work of Jormak. But then it was kind of questioned that which of these manifolds actually support UQR dynamics. And then kind of so that what we have is that so that in 2 dimensions, you have the possible targets are the 2-sphere and the torus, and then we know this is all classical. In kind of 3 dimensions, what you have is that you have the S3, S2 crosses 1, and then the 3 torus. And then comes the question that okay, so and then there are quotients. So that then comes the question that so where do you can push the UQR dynamics, and then the Astola, Kangaslampi, and Peltonen show that in all of these cases you have UQR maps. So that in this case the interesting manifolds are kind of S3, which is kind of the with the most richest, and then there is the S1 crosses 2, and now I noticed that you caught me that I didn't do my homework well enough to remember that what are the possible maps in that case. But there you can actually do the list. But then starting from dimension 4, the interesting thing is that so that you can classify the manifolds, the closed manifolds, which receive a quasi-regular map from R4. But then there is a manifold which I like to call a Riemann manifold, which was because the existence of the quasi-regular map was shown by Riemann, which is the S2 crosses 2 connected sum S2 crosses 2. And this is an interesting manifold because there is a quasi-regular map from R4, but it's a result of Kangasniemi that there is no UQR dynamics on that manifold, or interesting UQR dynamics. And it's an amazing result. And then it means that that means that in dimension 4 the game is open, so that it's not so that we don't know what is going on in that respect, and we also don't know so that what is happening in lower dimensions. You also know that whenever you have UQR dynamics, you also have lattice dynamics. But in dimension 4, starting from dimension 4, we don't know whether UQR equals lattice. And this would be actually very interesting to know because that would actually explain. My feeling is that would also little bit kind of also shed light about that why the list of quasi-regular elliptic manifolds looks how it looks like. So that because then kind of when you do that, if you know that all the dynamics is lattice, then you get also a mapping from the torus, which is kind of somehow the best possible map you can have in this case. So yeah. Okay, sorry for rambling so many things, but I am really interested in the question.
Thank you. That's actually really great. I enjoyed it a lot.
So Pekka, can you explain maybe again where exactly your condition comes in that the maps are, what do you call this? I mean, these cellular PCF.
Yeah, cellular. There is a. So I think kind of the right. I think this is the starting point. So because when we have a Thurston map, or this Thurston-type map, with this type of description, so that you have only these topological conditions and some kind of topological regularity conditions. So the key of all of that is to obtain the cellular sequence for the map. And then when you go, and then the cellular sequence starts to work like, so that gives you a kind of this type of shrinking decompositions, or so that the mesh goes down to 0 in this lower row, and because you have that, then you get visual metric. So that and then when you have the visual metric, you have a metric regularity for these maps, which is this branch quasisymmetric condition. And this is something that so that this is somehow the first step to where we really use the kind of the structure of the map.
But do you really need a cell decomposition? I mean, this looks like a strong condition, right? I mean, if I understand you right, is at the end of the day, I mean, all you want is this kind of shrinking sequence of covers so that you can define the visual metric, right?
Yeah, I mean, the visual metric should be able to define, with weaker assumptions.
That's
at least in
possible.
principle, right?
That's possible. So that That's actually, yeah, so, okay, so, yeah, perhaps I'm, okay, somehow I must say that I never really thought that you could go somehow beyond this, but perhaps you can.
I mean, you had these
Yeah,
two, like
yeah,
loops, and the
yeah,
first loop did not use, I
yeah,
mean,
yeah,
did
yeah.
use much less, right? And then the second
Yeah,
one,
but then kind of so that what you there where you start with this uniform expanding branch quasisymmetry,
yeah.
and you are, and that's in the standard metric. That's in the standard metric. So then comes the question that how the quasisymmetry of the identity is related to the dynamics in the kind of standard metric picture. And for that, I needed to go, or we needed to go through the kind of the that the dyna, that the mapping is kind of natural gives you a natural branch quasisymmetry in the visual picture. But you are right. So that if I now if you look just at the because I here omitted the equivalence of kind of 1 and 2. So that if you take that out of the picture, so there we use it. But then when you leave that out of the picture, then the equivalence of the conditions becomes more of a metric game, except that when you want to improve UQR to lattice. And when you want to, because if you just have a UQR map, then there's no guarantee that it is lattice, and you need to have some argument. So what is happening is that we are using the combinatorial structure of the map to actually get a kind of a property, which is that the index under the local index of the map under the orbit stays bounded, which is satisfied by the lattice map. So that when you have that, then the uniformization in higher dimensions, which is the Martin-Meyer argument, kicks in. Yeah. So okay, now I must say that the Mario's original question, that what you, so are these really the only places? So I must say that kind of the junior co-author would know the best the answer to this question, but
It's
somehow
already in the comment. It's
Yeah,
already in the
Hanyun, he made it.
there's already in the comments. The answer is already in the comments. It's good to have younger co-authors who know these things. But somehow these 2 points for me were the keys. Yeah. Yeah.
Okay, do I finally get a turn?
And there's sorry, I forgot that. Yeah.
So
Thanks, Hanyun. There's one more.
I kind of have to. I kind of was asking similar thing as Daniel, but sort of slightly. I agree that 4D is unresolved. Like for UQR, but for UQR, we don't know the connected sum of 3 copies of S2 cross S2. Yeah. But you have a lattice map. Is the 4D unresolved just because no one has really seriously attempted to classify the 4D situation for lattice maps? Or did you attempt this and run into like serious problems? Because like just off the top of my head, you know that you now have a surject, if it's not a rational homology sphere, you know that you now have a surjective QR map from Rn to that is regular under a group. So your manifold is topologically an orbifold quotient of R4 cross R4. Can you just like, what I think is the natural thing to try is that you would just check all the weird cases in Juran and Susanna's classification where we don't know if there's a lattice type map where is there some obstruction to presenting them as an orbifold quotient of R4. So has that been tried?
So let me just say that as you could hear from the question, the expert is the one who was asking the question. So that it's but I think that is the strategy nobody has tried. But I somehow based on the counterexample for the 2 copies of S2 cross S2, I'm expecting that you have to kind of I'm a little bit worried that you have to come up with some similar type of argument where there is some crazy product structure living on the cohomology of the manifold. So I actually find the question very interesting, and I haven't worked on it. And I think you are really the person asking the question. So Ilmari is really the expert here.